This is a wind tunnel in indoor skydiving, and you might think that there is a fan here blowing air up, making you fly. But actually, you'd be wrong. The fans are actually hidden in a completely different location. There are a lot of myths out there about skydiving, and that's why I created this video. The biggest, most in-depth video on the science of skydiving ever. We are going deep on this one, so sit back, relax, and enjoy. To show how indoor skydiving works, you can take a hairdryer and a ping pong ball and place the ball on top and turn it on, which can sometimes take some time. And eventually, it works! Many toys use this principle to make things levitate. And it doesn't even matter if I tilt the hairdryer, the ball still stays on. This is known as Bernoulli's principle. And it works by creating a region of low pressure area around the ball. This happens because if a fluid like air's speed increases, its pressure will decrease. And so, the surrounding stationary air has higher pressure. The higher pressure of the ball exerts a force pushing the ball back into the low pressure air, keeping it levitating. The air provides an upwards force against gravity, causing the ball to float. The ping pong ball will first fly up until it reaches this point of balance. You can tilt the hairdryer pretty far, showing how effective Bernoulli's principle is. But eventually, if you keep tilting, gravity wins. This is the same principle indoor skydiving relies on. A fan pushes air up in the wind tunnel, pushing the skydiver up, opposing gravity not with lift, but with drag. Air molecules bounce off you, pushing you up, making it seem like you're flying. But being lighter doesn't mean that you'll go higher, because the fan speed is adjusted to accommodate the weight of each skydiver. You can see this as my sister goes about the same height as me. The speed is changed by the person controlling the fan's speed. By the way, for this video, I actually went out to iFly to test out all of this, so special thanks to them. So, what exactly is drag? Well, as we discussed earlier, drag opposes motion. If an object is moving in the air, something is pushing it in that way. And if it slows down, something is making it do that too. That something is drag. But some objects are pushed around more than others. Bigger objects usually have more drag. This is because of their larger surface area. Bigger objects have more air molecules to push out of the way, and therefore need more force to counteract that. Smaller objects have less air molecules to push out the way, and therefore less drag. Drag doesn't just act sideways, but also upwards or downwards, like in our hairdryer and ping pong ball experiment. Here at the Queensland Museum, you can test this out with this fan, which is basically just a scaled down version of a wind tunnel in indoor skydiving. In my hand here, I have a smaller piece of paper and a larger one. The small one goes basically nowhere, and of course, the bigger surface area piece goes higher. There's more air pushing it. But what if I add these sort of helicopter-like designs to this paper? Well, here's one with larger blades, which goes pretty high, and here's one with less blades. Now both go high, but the first one went higher. This is because, as we talked about earlier, there is more air hitting the paper, and so it goes higher. Drag in this experiment is acting upwards. You can also show this by taking a crumpled piece of paper and dropping it at the same time as the normal one.
Jim, we copied both solar wind and penetrometer drum in the ETB.
At the end of the Apollo 15 moonwalk, Commander David Scott held out a hammer and a feather and dropped them at the same time.
hand I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Because there is no air resistance on the moon, the feather and the hammer fell at the same rate. Usually on Earth, we are surrounded by matter all the time. Even in this glass, which appears empty, still has air in it. Just 1 cubic centimeter of air contains about 30 quintillion molecules. However, what if you were able to remove all the air, suck it all out, like a vacuum? Which is exactly the name for something that does that. Scientists essentially suck out all the air of an object, creating a vacuum. The best done of this is about the density of 1,000 atoms per cubic centimeter. While this might not sound that impressive, do remember that a cubic centimeter of air roughly contains about 5.4 times 10 to the power of 19 atoms. So, pretty impressive. And now, back to air resistance. Wait, hang on. Haven't we already talked about this? A crumpled piece of paper falls faster than a larger one. More surface area equals more drag in a wind tunnel or without. Drag can affect objects in all directions. What more is there to it? Well, there is a problem. What if you drop a piece of paper at the same time as a washing machine? According to our rules, the washing machine should have more air molecules to knock out of the way than the paper, and therefore the paper should hit the ground first. But no way that's right. Now, I didn't have a washing machine to test out this theory, but what I do have here is a basketball and a feather. As you'd expect, the basketball falls far, far before the feather. The reason that some bigger objects fall faster than some smaller ones is because they fall based on more than just surface area. Shape, velocity, cross-sectional area, and surface texture can all affect the degree of air resistance an object experiences. In our experiment, which object, the feather or the basketball, experiences the larger amount of drag? The answer is not what you think. Even though it seems that the feather is clearly affected by drag, the ball is the object that actually experiences more drag. This is because, you can see here, because of its mass, it gets going much faster than the feather. And remember, drag is directly proportional to velocity squared. Since the ball falls faster, it experiences more drag than the feather. It's just that it weighs so much more that air resistance barely affects the basketball in comparison. If you look carefully, you'll notice that the feather floats down for most of its time at a constant speed, called its terminal velocity. This is the speed where the force of gravity down is balanced with the force of drag upwards. And as you probably know, when forces are balanced, objects either stay at rest or move at a constant speed. The basketball never reaches terminal velocity when dropped from here, and so it continues to accelerate until it hits the ground. The feather, on the other hand, reaches terminal velocity much earlier, and so after that it just moves at a constant speed. Every object has its own terminal velocity, which is the fastest speed an object will reach when in free fall. Here are 8 people in a wind tunnel. You'll notice that they are floating at similar heights. This is because they have the same size and shape, so they experience the same amount of air resistance. If one is heavier though, then it has a higher terminal velocity, and so it floats at a different speed in a wind tunnel. At first, it may seem like hail, the lumps of ice that fall from the sky, can't be very dangerous. Usually in the US, there is an average of about 7 to 9 hailstorms per year, but approximately 24 people are injured each year from it. But why is this? Well, hailstones can reach speeds of up to 60 kilometers per hour, but it is also because they can reach terminal velocities of up to 200 kilometers per hour. But what makes its terminal velocity so high? Well, something to think about is how big it is. The largest hailstone ever recorded was in 2010, which had a diameter of, no joke, 20 centimeters. Now remember, drag is also proportional to cross-sectional area. This is important because a hailstone's mass is proportional to the cube of its size. But since the area of a circle is proportional to radius squared, so the cross-sectional area is also proportional to r squared. And so, hailstones fall at high terminal velocities because their mass, which is proportional to the cube of their size, increases more rapidly than the cross-sectional area, which is proportional to the square of their size. This means that larger hailstones have a greater downward force compared to the upward force of air resistance, leading to faster descent, which means the larger hailstone, the higher terminal velocity it has, which is what makes hail so dangerous. When a skydiver first jumps out of a plane, there isn't much drag acting upon them, but as they keep accelerating, the drag force grows larger and then stops growing when terminal velocity is reached. Skydivers can control how much drag they are exposed to by changing their position. This is what skydivers do in order to catch up to those who have exited the plane before them. You can change your body position to control your falls. This can be done by presenting less surface area to the air molecules, reducing drag, and so you go faster through the air. But you can use drag for other things as well. If you move your arms to your side and spread your legs out, there is now more airflow at your feet, which pushes your body in the direction you are facing, moving you horizontally. This is a skydiving technique known as tracking. Since fewer air molecules hit you when you try these different positions, you can go much faster than before. Skydivers can reach speeds of up to over 300 kilometers per hour. Obviously, you don't want to hit the ground at over 300 kilometers per hour, so skydivers use parachutes. Since you cannot change the pull of gravity, you need to increase your drag as much as possible. So, you can open a parachute. Skydivers use parachutes at the end of their dives, as they increase the amount of surface area that's facing the air, which slows them down and allows them to land safely. In indoor skydiving, wind speeds can be pushed up to about 300 kilometers per hour. Everyone has their own wind speed that they fly at. Indoor skydiving is the equivalent of reaching terminal velocity in freefall. Based on my experience, I must say, it didn't really feel like I was flying or weightless, probably because I could feel the fan blowing upwards towards me. Professionals use higher wind speeds as they allow you to make quicker moves. What you're wearing can also affect how high you go. Most beginners wear a baggy suit, as they'll put you on a lower wind speed, because there is more drag. Most freestylists use a tighter suit, as they are on a higher speed. Here, the instructor is on a higher speed, and is very, very good at indoor skydiving. I mean, just look at him. And yes, he did just backflip out of the door. Wind tunnels have been around since the 1940s, but the first ever person to fly in a wind tunnel was Jack Tiffany in 1964 in the Wright-Patterson Air Force Base, used to test aerodynamic research.
At Wright Field, at the headquarters of the Air Materiel Command, aeronautical engineers work on problems of research and development. By studying the behavior of model planes in the vertical wind tunnel, they discover how pilots can pull out of dangerous spins or bail out safely from fast jets.
Early wind tunnels were often used for testing aircraft, but nowadays can be used for indoor skydiving tunnels. You may think that this here is a fan below the skydiver. Well, actually it isn't. Wind tunnels rely on a much more complex system. Early tunnels did feature the fan below design, but were phased out in 1997, when a patent for a wind tunnel with the fans being moved above, pulling air up instead, and the chamber to be enclosed. This is known as an open flow design, which used engines to pull the air upwards through the flight chamber, literally sucking it out from the outside air. But in 2004, we got the modern wind tunnel design we have today. Each building has a recirculating system instead of pulling air from outside. The air was contained in a closed circuit loop. At the top, there are 4 giant fans which pull the air up through the tunnel. Then, the air recirculates here, separates, and comes back up again. This means that there will be less turbulence and more controllable wind. But how does this achieve this? Well, it's because of these things you might mistake for being a fan, called vanes. These vanes turn the air to go past these corners, and they are aerodynamically designed to bend the air smoothly. And because of these, wind tunnels typically generate about 28,000 cubic meters of air per minute. So basically, hurricane-like winds going right at you. And so, contrary to popular belief, the fans are not at the bottom of the tunnel. They are placed at the top for more efficient speeds. What's even cooler is that the turbines only produce a wind speed of about 32 kilometers per hour. The reason that they are able to generate 160 kilometers per hour winds is that the diameter of the glass chamber is much smaller than the path it takes to get there, meaning the speed of the airflow increases dramatically as it's forced into a much smaller tunnel. Air then flows up back to the top of the building, whereas recycled back into the turbines, basically compressing the air to create higher PSI. Drag, as we talked about earlier, depends on a lot of factors, including shape. This is measured using a dimensionless quantity known as drag coefficient, which essentially measures how streamlined an object is by how smoothly air can flow around the object without creating disturbances. It's represented with the letters CD. The word bullet is from the French word boule, which means ball. A boulette is a small ball. This is just like how the first bullets look like. But people realized that the drag coefficient of a sphere is not very good, only 0.5. So they modified the shape to reduce drag, making it more aerodynamic. And that's how we got the modern bullet shape, with a drag coefficient of only 0.1 and 0.3, making it much faster. In January 2010, a team of scientists were trying to attempt the highest skydive ever, with a helium balloon. More than 2 years later, on the 14th of August 2012, Austrian skydiver and daredevil Felix Baumgartner flew 39 kilometers into the stratosphere before free-falling in a pressure suit. This made Baumgartner the first ever human to break the sound barrier. He reached a terminal velocity of 1,357 kilometers per hour. But how did he go so fast? Well, at that altitude, there is much less air than down here. This is because air resistance is also proportional to the density of air itself. And because he was so high up, the air was 60 times less dense than Earth, so he went very fast. As he kept falling, his speed lowered. There's more air resistance as you go down, and so, at 2 kilometers above sea level, he was only at 200 kilometers per hour. Now I know this section on drag has certainly been dragging on, so let's answer another question we promised in the intro. Remember the hairdryer experiment early in the video? Well, here is a similar setup to before. Alright, For this experiment, I have the hairdryer as before, the ping pong ball, this container which is going to hold it up, and over here is a scale. What I'm trying to show is if you were to put a ginormous scale below the ground, let's say as we hopped into the wind tunnel, would the ground feel our weight? Or in other words, would the scale increase? Since this is basically a scaled down version of what's going on there, we can test this out for ourselves. So the ball is representing you actually going into the wind tunnel. And of course the hairdryer is the actual fan. The current mass of the ping pong ball is 2.76 grams. So if the scale does increase, it should increase by this much. Alright, let's turn this on. So, what do you predict? Will the scale increase, decrease, or stay the same? If you thought the scale would stay the same, well done. But why doesn't the scale increase? Whether or not the ball is floating on the air, the weight on the scale doesn't increase. First of all, the reason that the scale shows 591 grams on it in the first place is because of Newton's third law. Every action has an equal and opposite reaction. The hairdryer pushes air upwards, so throwing a lot of mass upwards, and so the hairdryer is therefore pushed down because of Newton's third law. Just like when you press down on a scale, the weight increases. When the ball is placed on top, it is supported by the air coming out of it. You can think of these as little balls which represent air molecules shooting out of the hairdryer and keeping the ball afloat. Like we said before, the hairdryer is already being pushed into the scale and it doesn't seem to care whether the ball is there or not. So imagine the ball's coming out of the hairdryer again. When we put the ball on, it's still being pushed down. But the little balls would be able to hit the ping pong ball above it and transfer their momentum to it. However, this doesn't translate to the scale below. The ball doesn't affect the weight because the weight on the scale is only dependent on the weight of the hairdryer and the speed and momentum of the air being pushed out of it. The ball is essentially decoupled from the system. Another reason this occurs is because although the hairdryer is being pushed down to the scale, the air it is shooting at is constant in velocity. No matter if a ball is on top or not, it will always be throwing air at the same volume and speed. Now there is a practical application for this, but for that I had to bring in an expert.
Hey YouTube, I'm ThatRocketKid. I'm someone who really likes rockets and has done some attempts building them, though not so successfully. The amazing people over at South 6 have reached out to me to do a section on rocketry relating to this topic. Now you understand how this experiment works, I'm going to show you a useful application of it. Rockets. The basic principle on how rockets work is Newton's third law of motion. Every action has an equal and opposite reaction. By throwing as much mass or weight out the aft end, which is this bottom part here, with as much velocity or speed as possible, it will accelerate the vehicle up with the most amount of thrust.
Rockets don't need a launch pad or anything to push off from. Instead, rockets generate thrust by expelling hot gases out of a nozzle, and this action causes the rocket to be propelled forward. The action is the expulsion of hot gases, and the reaction is the force that propels the rocket forward. While we often think of pushing off a surface like when we walk, rockets don't need a surface to push off against. The exhaust gases themselves provide just that. The principle works the same way in the vacuum of space, where there is no air to push against. Rockets carry their own fuel and oxidizer, like liquid hydrogen and oxygen, and can generate thrust to move through space. It's amazing how simple experiments like these are the core to understanding the most advanced of things. And that there is the beauty of science. This was definitely the most time-consuming and longest video I've ever done, so if you enjoyed it, then it would be greatly appreciated if you could like and subscribe. Just like all of these people, thanks to all of you for subscribing, and if you would like a shout out in the next video, then make sure to subscribe. Also, if you did subscribe but your name isn't listed here, make sure to navigate to your YouTube settings, then Privacy, and uncheck the box that says keep all of my subscriptions private. There's a video in the description if you want to know how. If this still doesn't work, then please get in touch so your name can be listed next time. And now for the credits.